Welcome and hello. This is a video tutorial in HEC RAS, and in this lesson, I'm going to be discussing sediment computation options and tolerances. So where that is in your HEC RAS is I have the sediment transport analysis dialog box open up here. I can also click on the stick figure running on sediment or access that going to run quasi-unsteady analysis sediment. All right, so what I'm going to be talking about in this lesson, in this video, is options, sediment computation options, and tolerances. And then I'll be discussing the different options available in this dialog box and how you can use them to fine-tune and improve the overall quality and runtime and stability of your quasi-unsteady simulations in HEC RAS, which are used for sediment transport. All right, so let's go ahead and get started here. The first one is bed exchange iteration per time step, abbreviated SPI. I think that's a carryover abbreviation from a previous HEC RAS version. The default value here is 10. The mixing and armoring algorithms update multiple times per computation interval. So this number here is the number of times that mixing and armoring algorithms update. So for instance, if you have a 10 value right here, HEC RAS will update the mass and gradation of the bed layer every 10% of the computation interval. So yeah, if the computation increment is 1 hour, and then I had a 10% right here, then the bed layer will be updated every 6 minutes. The range of values here is recommended between 1 and 50. So I think 10 is a good middle of the road default value to start you off on. The user manual mentions to start this number high and then decrease it as long as your results are the same. That way it will improve the run speed of the simulation without compromising results. All right, the next value down is the minimum bed change before updating cross-section, and that's in feet. This is a tolerance value, just like the one below it is also a tolerance I'll be talking about in a moment, but it's set by default to 0.02 feet. Once this minimum bed change is achieved at one of the cross sections, the bathymetry is recomputed, not necessarily every computation interval. Recomputing the bathymetry is a rather computational intensive process compared to a normal time step for calculating hydraulic data. And that's why this tolerance value is set right here. You may not have to recompute the bathymetry with every computation interval. The larger you set this number, the less often that bathymetry computation would have to take place. That means larger numbers would mean it's less sensitive to bed changes, and also less frequent changes means there's fewer computations and faster runtime. Now, the smaller you make this number for minimum bed change before updating the cross section is just the opposite effects. It will be more precise. There will be more recomputations of the bathymetry and the cross section, but that may cost you longer run times when you click compute. All right, the value just below it is another tolerance value. This is the minimum cross section change before it recomputes hydraulics. So just because the cross section changes doesn't mean that hydraulics will be recomputed unless that change is more than this tolerance value here. Again, the default value is 0.02 feet. Hydraulic parameters are not automatically computed after each computation increment unless one of the cross sections has undergone pre-sheet of change, such as beyond this 0.02 foot. Every time the cross section changes by at least this 0.02 feet, the hydraulics are recomputed. All right. There's also a checkbox here. It's checked on by default. And what it says is it recomputes the volume air after bed change and carry over into the next time step. Next up is this transport energy slope method. And then we have a few different options here: local, downwind, and average. This selected slope does not affect the hydraulics, but it does affect the sediment transport. So let's talk about each of these briefly. The first option here is the default. This is local. The local version uses only the current cross-section and Manning's equation to determine what that slope is. So if you remember Manning's equation, if you know let me get it up on screen here. Okay, here's the page with that information. Here we selected local. Here's a description of the three different, we'll go back to that. Here's the equation. So you just rearrange Manning's equation for the slope and solve for that value. So it only takes into account the current cross-section of interest, which for this example, they're using River Station 2000. All right, back to HEC RAS. The other two options here is downwind and averaged. I'll talk about averaged or centered first. So let's go back to the user's manual here, or the HEC RAS 1D sediment transport document. If I scroll down to average, here we go. This method takes into account a slope using 2 points on the energy grade line from the computed hydraulic results. So one point is upstream of the point of interest and another point is downstream of the point of interest. Here's a little diagram here. If our point of interest is this river station 2000 and we set a 100-foot distance upstream and downstream, the denominator is the sum of those distances, 200 feet. And then we take the energy grade line value at those 2 points and then use those for our vertical datum. So the difference here would be the numerator. That results in 0.0027 for a slope. And then the last option here is the downwind option. This takes into account the current location as well as the downstream location. So this looks similar to what we saw, except we're only using a downstream location, which in this example is 100 feet away, and then just computing the slope based on the energy grade line at the point of interest and that downstream location. And right here is the math for this example. All right, let's go back to HEC RAS here. The next thing to talk about here is the sediment computation multiplier. This is a way to improve the speed and efficiency and runtime of your quasi-unsteady sediment simulations. The hydraulic calculations often require smaller time steps than the sediment calculations, and for that reason, if the sediment uses this time step, the same value, then it could take a long time unnecessarily. That's why we have this multiplier here. So the sediment time step could be a certain multiple of the hydraulic time step. By changing the sediment computation interval to be a multiple of the hydraulic computation interval, that's what we do right here. This solves the problem of too many unnecessary sediment computations. So as an example, if the stable results for the hydraulic computation interval is, say, 1 minute, and we set this value to 60, then that means the sediment computation interval will be 60 minutes or 1 hour. Below that, we have sediment warm-up period available. There's concentration for 2D, but for both methods, there's gradation and bathymetry. Current versions of HEC RAS include a warm-up and hot start options to deal with early simulation cross-section adjustments. So you just go ahead and type in the number of days in these fields right here. All right, below that, we have dynamic bed roughness, starting with a bed roughness predictor. So the default value here is none, but there's a few different options. There's none, Lee Marinos, Brownlee, and Van Ryn. These are various methods of how to vary channel roughness values with Manning's N values with respect to space and time. And it's based on values such as flow rate, stage, lateral station, season, and also based on the sediment dynamics. So if I select Lee Marinos, for instance, this is a simple method based on the D84 grain size and the hydraulic radius. It's most applicable to coarse and gravel channels. The next one down is the Brownlee method. This takes into account low and high sediment transport regimes based on the bed form mechanics, and it's used for larger rivers. And then the last one here is Van Ryn. It's based on flume and field data. It's used for both dune and plain bed regimes. So that's what the user's manual told me about these. And then towards the bottom of this dynamic bed roughness frame, there's a button labeled here for select reaches to average bed roughness predictors. This tool is used to smooth out the effects of potentially erratic roughness changes along a river reach. So here's my river reach off to the side from 1000 down to 0 as my river station every 100 feet. I would use this tool right here to compute a single bed roughness for all cross sections in a certain range based on the average hydraulic and sediment parameters within that range. So I'd set the range by clicking on this button here, and then a dialog box pops up. I'd select the river, I'd select the reach, and then I'd select the range of adjacent cross sections. And then, like I mentioned, a single bed roughness for all those cross sections will be used using the average of these values. So what I would do is, upstream would be 1000. We'll say the downstream end of this group is 700. I click set bed roughness reach, and then it adds a row here to the list box. So let's go ahead and do the same thing now for 700 down to, say, the bottom of the reach, which is River Station 0, set bed roughness reach, and we're good to go right there. This should probably improve the situation if your sediment model has instabilities. Another way to reduce instabilities, for instance, if you have a quasi unsteady model for sediment and every other cross section is eroding, depositing over and over, and you get this unnatural oscillation that you know wouldn't really happen, click on this button here for Show Cross Section Weights. This is another method to perform averaging and prevent those sort of unnatural oscillating behaviors. HEC 6 introduces cross-section weighting factors to smooth out these effects using cross-section weighting factors. So that's about all the user's manual says about this side panel and the values, but you can pretty much glean what it's trying to do here. There's some parameters here for the internal cross-section, like the cross-section of interest, and then upstream boundaries and downstream boundaries. So if you wanted to average the number of cross-sections upstream of, say, River Station 500, say you wanted to add like 600 and 700, you'd say the next two cross sections, the number of downstream cross sections to use for averaging. If you wanted to go down to say 300, you'd type in 2 right there because we have 400 and 300 is the first and the second one downstream. And then for weighting factors, these would sum to 1, and the value would for each of these text boxes would be between 0 and 1. So for instance, I could say 0.25, 0.5 for the main cross section, that'd be 500, and then 0.25 for all the downstream cross sections. So anyway, this is sort of an averaging tool to help smooth out any instabilities or roughnesses within the sediment results from your quasi unsteady simulation. All right, so you can close that back up right there by clicking that button a second time. Also at the bottom, there's this button for defaults. You can reset the default values here by clicking on the default button right here. And that is about it. This is the end of our lesson where we talked about the sediment computation options and tolerances within the sediment transport analysis or the quasi unsteady flow analysis in HEC RAS.